So this is a bit of the tricky part, is overlaying these on top of one another. But here I've just copied and pasted, and you can just go ahead and draw over the top of one of these graphs. But these are my X nullclines in green here, with my arrows drawn within each of these 4 regions. Now I'm further going to subdivide this by taking the Y nullclines and also plotting them on the same set of axes. So that means that what I'm going to do here is take this guy, and plot 3 minus 2x on top of this graph that has the X nullclines in it. Or you could do it vice versa, it doesn't really matter. So 3 minus 2x, we said we'll go through 1, 1, and 0, 3. So let's see if I can draw this well. Not really, but we're getting there. Let's see. So this needs to go through 0, 3, and it needs to go through 1, 1. So we're getting pretty close there. And this doesn't need to be perfect. This is just for illustrative purposes. So here you can see that these two functions intersect at the point 1, 1. Well, that's a Y nullcline and an X nullcline intersecting one another. And we said that when Y is in a nullcline state and X is in a nullcline state, that's an equilibrium point. And so you'll notice that that is actually one of our equilibrium points. That's the equilibrium point 1, 1 that we obtained right here. Very nice. So it turns out that there is a connection between nullclines and equilibrium points. I just want to adjust this just a little bit because it's kind of bugging me. There we go. That's better. Whoops. Was better. There we go. Battling technology. Okay, there we go. And so I'm also going to plot this second nullcline here. I'm going to go ahead and grab this, or I could just plot it again. And now I'm going to be really careful because now I see that depending on what region we're looking at, everywhere, if I just look at the green nullclines, those are my X nullclines, then I know that everywhere within this compartment, ignore the pink for now, everywhere within this first region, the top right portion, which corresponds to what we came up with up here, everywhere in this top right portion, I'm going to have vectors that point left. So what I'm going to do is I'm going to erase this right here, and I'm going to use green for consistency. And so that means here the vectors will point left. Also here the vectors will point left. And the reason I'm drawing another vector here is because there's a Y nullcline, which means when we jump over this nullcline, the upward or downward component of the vectors could change, and that's why I'm drawing another left-facing one here. Also, right in this little pocket here, I'm going to draw a left-facing vector, because again, that's where the flow is in that direction. And then everywhere in this green portion, the vectors are pointing right, so I'm going to erase this guy here and actually just go ahead and draw a two right pointing vectors, one here and then one up here as well. So that all I'm really doing is just kind of populating in those vectors where they need to go. Now everywhere in this portion, the bottom left half, the vectors point left, and so now it's been subdivided into 2 regions because of the pink vector. So here there's left pointing vector, here there's left pointing vector, and so that covers me everywhere within this region, which corresponds to what we called region 3. So we've just basically labeled the top half and the bottom half. And now also we have this fourth region over here, and the vectors point right everywhere down here. So I'm going to erase this right pointing vector and put it in all of those little pockets. So here, 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 oops, and here as well. Okay, now you're probably guessing, well, what's coming next, and that is to label the vertical component of those vectors. So now we have to focus our attention on the pink lines, and everywhere within pocket 1 of the pink lines, there's going to be downward pointing vectors. So that means everywhere within this region, above this region, we're going to have downward component vectors. So that means here I'm going to have a downward component. That means here, this vector is going to have a downward component. So let me really zoom in there. And that's going to have a downward facing component. Let me go ahead and redraw that. So that'll point right, and then we'll have a downward component there. Now we can go ahead and zoom out a little bit, and that covers us within that region. We also know that within region 2, we're going to have upward pointing vectors. So region 2 is everywhere within the bottom right portion of that. So those are going to be upward pointing vectors. So I'll have an upward pointing component to this guy and an upward pointing component to that guy. Now within region, what we called region 3, which is everywhere in the bottom left, there's going to be a downward component, pointing component of that vector. So see, that's going to be here, it's going to be a downward facing component, and here, because we're still in the same realm of those two y nullclines. The reason we drew those two green vectors, or those two pink vectors, is because here trajectories flow down and to the left. Over in this pocket, trajectories flow down and to the right. So that's why we continue breaking these up into further regions. And finally up here, everywhere up here in this top left portion, there's an upward facing component to that vector. So this guy will have an upward facing component, this guy will have an upward facing component, and this guy will have an upward facing component. Also this guy here as well, because again, we're on one side of that nullcline. So let me zoom out a bit, and we've already said that there are 2 equilibrium points, or 4 equilibrium points. There's one there, there's one there, there's one where any 2 different colored lines intersect, so 2, 0, that's another equilibrium point, and 1, 1 is our 4th equilibrium point. Oh, I'm sorry, not 0, 2. 0, 3 is actually an equilibrium point. That's where those 2 nullclines meet, those 2 nullclines meet, those 2 nullclines meet, and those 2 nullclines meet. Now we know that 1, 1 and 0, 0, 1, 1 acts as a saddle, 0, 0 acts as a source. So we know that initial conditions anywhere will never end up at those 2 equilibrium points, but some do end up at 2, 0, and some do end up at 0, 3. So imagine that there's a point inside of here. Where can that point go? Well, that point can only move down and to the right, down and to the left, excuse me. So it can't go up, and it can't go to the right because of how the signs of dx dt and dy dt. So this point is free to move down and to the left. Now, whether it's exaggerated, we can't tell based upon that, but this trajectory can flow this way. But what happens if it bumps into this? Well, that is a y nullcline. That's going to be where the y value is 0, where the rate of change of y is 0. So that means that we see that there's a left component to the vectors on the right side of this y nullcline, and there's a left component to the vector on the left side of this nullcline. But you see that whenever you jump over this pink nullcline, the vectors have an upward facing component, but to the right they have a downward facing component. So it turns out that because dy dt is 0 all the way along this thing, but dx dt is positive, we can see that this point can pass inside of this region, and now we're limited to behavior that is up and to the left. So you can see that one thing that could happen is that point can go into that equilibrium. Another thing that could happen is perhaps maybe it hits one of these walls first. What happens if it hits that? Well, that's an x nullcline. An x nullcline is where dx dt is 0, and you can see that the 2 horizontal components of the vectors point at each other, which means that once you get to this, the dx dt is 0, and in terms of the y component, we see that on the left-hand side of this y nullcline, all the vectors point up. So even if a point did hit this nullcline, it would travel up and hit that equilibrium point. Pretty cool stuff. Another thing that can happen is, let's imagine that there's a point inside of a different pocket. So let me erase some of these guys. The point starts in here. Where can it go? Well, based on the behavior inside of this pocket, it has to go up and to the right. Now, one possibility is that, well, does it go to the 1-1 equilibrium point? It can't do that because 1-1 is a saddle, and so it can approach 1-1, but it's never going to get there. So one thing that can happen is this point can travel up, and let's see, what happens if it touches that nullcline right there? Well, that's an X nullcline. You can see that below that X nullcline, vectors point to the right. Above that X nullcline, vectors point to the left. On that X nullcline, the vectors only point up or down, and we see that both above and below that nullcline, the vectors point up. So this point can pass into this region like so. Now it's broken through. I guess it would break through more vertically like that, and now this point can either hit that, but either way, it's going to be relegated to go into that equilibrium point. So we have all this power now in determining what is the likely trajectory of that point. Now, another thing that could possibly happen based on the information that we have now is this point goes up and to the right, but breaks into this region. And if it breaks into this region, now it's going to move down and to the right, so it can move and hit this nullcline here. But what happens if it hits this nullcline? Well, that's an X nullcline, meaning it can't pass to the right of that because dx dt is 0 on that green line. And you can see that the right and left arrows point at each other across this green nullcline. And so the only component that we see that's consistent above and below that is the downward pointing arrow. So it would actually be forced back downwards. And perhaps it hits this red line, but this is a Y nullcline, and we see that everywhere below this green line, the vectors point right, so that point is going to have to end up at 2, 0. So some of these points are going to go, that start off in this pocket, may perhaps go to 0, 3. Some of these may go to 2, 0, but it seems to be the case that all of them will have to go to one of those 2 equilibrium points. How we decide that? Well, I don't think we have total enough information to be able to distinguish between which one these will go to, but we do have more power now knowing that. Now, all initial conditions in here, in this third quadrant region, will all have down and to the left pointing behavior, and we saw this in our phase plane. This is just going to be forced that way. There are no other nullclines there, so since this vector has to travel down and to the left, it will do so indefinitely. And we can kind of make up similar behaviors for all of these other pockets as well. Let's go back and look at the phase plane for a moment to see how well this agrees with what we observed earlier. So here we have that phase plane, and we definitely see that what's happening in this bottom left portion, all of those vectors you can see here have a left pointing component and a downward pointing component. So all of these vectors point left and down. Some of them point more down than to the left, like these guys here, and some of them point more left than down. But that's not what this analysis is about. We're just trying to understand the qualities of those trajectories. Now, inside of the other regions, we just determined that, for instance, in this pocket, all of those vectors, notice here, they point to the left and up. But at some point, it appears that some of these points in here, right, they can hit this green line. Now that's an X nullcline. That's where dx dt is 0. So because above and below that X nullcline, we see, the vectors point right here, the vectors point left here. The only thing that can happen is if a trajectory hits this green nullcline is both of those arrows point up. So that point will push into here, which is what you see with this wraparound taking place. And I think there's probably some wacky stuff going on here because our step size is too big. There we go. That's a little bit better. And so what actually happens is this point breaks through here. Now all those vectors point up and to the right. And when it hits this Y nullcline, we forgot to label the vectors right above here. Those point down as well, since that's to to the right of this nullcline, the points kind of come up like this. They break through here, point to the right and up. They hit this Y nullcline. The green arrows all suggest that that point's going to go through here. And now that point has to move down and to the right. Well, what if it hits this nullcline? Well, that's an X nullcline. We see that the arrows to the left and right contradict each other, but the downward component faces down, and so that point has to end up there. Such a super powerful analysis that we can gain from this, and we see that happening over here. Down in this pocket, you can kind of see that those points go to 2, 0, and then some of them here, we saw that the arrows over in this region point down and to the left, and that's indeed true. Some of those we said are going to end up at 2, 0, and some of them are going to end up at 0, 3, and you can see that there's sort of this point where those two behaviors vary. And why does that vary so much? Well, it has to do with this 1, 1 equilibrium point, that some of these trajectories come this way but actually pass through like this and make their way up here. And some of those that are just a little bit too low come down and to the left and hit this nullcline and then veer right into the 2, 0 equilibrium point. So we just gained a lot of powerful information from this. And that was all just by looking at signs of vectors, which was a lot more than what we had before. So let's go ahead and take a look at one more example.